Hello again everyone. Before we get started, just a very quick opportunity for you to make sure you've got everything right. So just like with last lesson, please give it a go by drawing the solid, liquid and gas of the particle model. And when you're ready, press play. So hopefully you've got it right this time if you didn't get it right before. So as a very quick reminder, all these should be touching without overlapping like I've drawn, and a fixed shape. Gas is then the second easiest one, and it's liquid that people struggle with, so maybe take a little bit more time. So you've got them all interconnecting, but there are definitely gaps between a few of the particles, but otherwise they're all linking together. So today's objectives: draw a model of liquid confidently, so hopefully you've just done that. We also need to be able to convert confidently between degrees Celsius and Kelvin, so hopefully that might be a little bit of a repeat from last lesson. We'll look at the key features of solid, liquids and gases, and that's in terms of bonds and the energy between the bonds. And there's this thing called Brownian motion, which if you're in school would do a practical, and I'll be honest with you, it never ever works, so you're better off doing it remotely anyway. But what we can use it for is to provide evidence towards something called the kinetic model. So again, a quick check. What are 0 Kelvin, 27 Kelvin and 300 degrees C in their opposite value? So press pause, and when you're ready, press play, and we'll just double check the answers. So the first one, and a good place to start actually, is always refer to 0 Kelvin as minus 273 degrees Celsius. 27 Kelvin is then minus 246 degrees. And finally, 300 degrees was 573 Kelvin. Now, if you made an error here, then I strongly recommend re-looking back at the previous video where I just went through the conversion between the two. So we'll look at kinetic theory of gases, and there's this thing, as I said at the start, called Brownian motion. Now in a minute you'll need to go and have a look at some YouTube clips about Brownian motion so that you can see what it is and what the practical should have told you. But first, kinetic model. So it's something that describes how substances are made up of atoms and molecules, and they're arranged differently depending on the phase of the substance. So we know about phases, hopefully, solids, liquids and gases, and how they move depends on what phase that they're in. So we know that solids move on a fixed point, just backwards and forwards. We know gases fly around and their velocity or speed is high, and then we know that liquids are probably in the middle. Figure 2 in your book on chapter 14.2 goes through some of the key things, so please have a read through those so that you're very familiar with the different terms and the different structures that each phase gives. The key point to note about liquids though are the atoms are still really close together, but they have more kinetic energy than solids, and they can change positions. I'll try and remember to put these YouTube clips as a link rather than expect you to copy and put them onto Explorer to find. But do have a look at these two YouTube clips just going through this thing called Brownian motion. This is the practical that you will have given a go, and as I said at the start, seen nothing, but it's worthwhile, if we can get it done over the course of the next year, doing so just to help you visualise what on earth's going on. But you're obviously looking down a microscope just here, but when you look at a microscope, what you do is you're only looking at one plane of something, and then darting around up and down, left and right, you've got lots of particles. And because we've got a light that's shining through the area, when one of the specks of dust passes through the plane that you're focused on, it shines up as a little speck of light. And by looking at this, what you see, or should see, because it never works, you should see lots of flashes of light, and that's the particles moving. But with this, you need to be really clear what particles you're looking at. Now, in this case, you're looking at smoke. With Brownian motion, the original one, you're looking at pollen grains. What you're not seeing are the air particles, but there's then an assumption made that what the air particles are doing based on the smoke that you're observing. So if we zoom in, what we've got here are a number of smoke or pollen grains or particles, and they're the large ones. And then surrounding them, you've got a lot of smaller particles that you can't see, and we would call those air particles. Or if you're looking with pollen, there'd be water. So what we've got happening are these particles are moving around in a haphazard way. When they collide with one of the larger particles, it's perfectly elastic, so the kinetic energy is conserved. But we've got lots of these particles bombarding the smoke or the pollen from lots of different angles, and what we end up seeing are the smoke or pollen particles moving as a consequence of the lots of air particles or water particles passing the momentum or transferring the momentum from one to the other. So because all of the smaller ones are colliding with the big ones, we end up seeing the smoke move rather than the air or water particles that are causing the movement. And through the microscope that I showed you on the previous slide, it's the yellow ones that would flicker as it passes through the plane that you're looking at. So based on this, there can be some assumptions made. Movement of the smoke particles is caused by the randomly moving air particles. Smoke particles are continuously moving because the air molecules are also continuously moving. Smoke particles are visible, but the air particles or molecules are not, hence the air molecules must be very small. And finally, the small movement of smoke particles is due to the large number of air molecules hitting from all sides. So please spend some time looking at the summary questions on 14.2, and I've also attached a question for you to have a look at based on Brownian motion.